what this little is, right?
Right. My question though is, do we have to know that up front when you're doing this, or can it be open-ended? How does it handle that? Because it's program dependent actually. So how can it still handle that?
So I would say in this case, this E is also not like about a specific set of E's. Like you can also consider this as something that you can extend with more kinds of effects for. But ultimately, that again, we want to reason that whether that set of axioms are respected, and also if the race operation is still algebraic, then this equation should hold. So it does not matter what this little is.
I see. Thank you.
So let me do something stupid. Like let's say I wanted to say here I have an effect that encodes addition. Right? You would not do this. I'm just trying to test out the plausibility of this definition that's on the slide.
Okay, you have an effect of what?
An effect that encodes addition.
Addition.
Yes.
Okay.
So it takes two things, right, and then it kind of adds them, right? I'm just wondering here with this definition, like if you had some operation that like increments, it just adds one, like an evaluation context that does that, and when you push it down, it seems like this would mess with the semantics of an effect like this.
Well, if it doesn't hold, then the operation is not algebraic.
Okay.
Then the class is not algebraic.
Yeah,
So
let's say you would do that in practice. I was just wondering like how far this goes.
So this only talks about operations being algebraic, but of course you can have different operations where they have different semantics, and this one doesn't say anything about that. And as we will see, I think the algebraicity is partially built into the operational semantics once we get into that point. So if we actually define something like that, I think it should still hold because your definition of add, it does not follow exactly the signatures because the signatures would usually say that it takes two computations, but it doesn't try to add them together to some degree. It's more like you would choose one of the operations, okay, you could run both of them, but they generally do not interact with from all the examples we have seen.
Yeah, I don't know exactly how it encodes. There should be three arguments, like it would evaluate the two first and then pass the value to the third, or and then I'm just wondering when I push down like an incrementation evaluation context, it seems like it would add one to the first, and add one to the second, so that should add two to the third, but it only adds one to the third. Do you see what I'm getting at?
I think the best answer is probably the operation is not algebraic. And it's completely fine for the operation to be non-algebraic. It's just non-algebraic.
And could you repeat what you mean exactly by algebraic?
Is this equation holds.
Okay, all right. Sure.
Okay. But of course, if you want more detailed definition of algebraicity. Okay, so to recap, what we have talked about. We have talked about an algebraic effect given by a set of operations as effect constructors, and they come with signatures, and there are a set of axioms that we expect them to respect, but sometimes they don't. And there is this definition of algebraicity when we say operations are algebraic if they commute with evaluation contexts. Next, before we talk about effect handlers, I would like to briefly talk about computational trees and free monads and generic effects. I think I should be able to finish computational trees at least before 5. Okay, so computational trees and free monad. So sometimes people say that computational effects for computation is a tree. I don't know if you have heard about this. So what does this mean? So recall that we have seen this example with Boolean locations with signatures. So put T and put F have arity 1 and get has arity 2. And we can write an example program with it. For example, we can define toggle, which says I'm going to get the value And if it's true, I'm going to put F and then return true. And if it's false, we are going to put put T and return F. So question, what is this term doing? Mm-hmm.
Actually, I don't know.
Uh-huh.
It gets an it basically it gets an if it's true, it puts false, and if it's false, it puts true.
Right, so it flips the value in that memory location and it returns you what the value in the memory location is before you flip it. Okay. And now, so this is how we would write it in a program, right? And how would we represent it as a tree? Okay.
Get is a node with two children.
Ooh, okay, great. Yeah. Spelling out my next slide. But okay, so more generally, what is a computational tree? So in this case, I will represent values with triangles and operations with rectangles, and you will see they have children. And we say that a computational tree is a tree whose leaves are values and internal nodes are computations. So going back to our example, this is how you are going to draw this program as a tree. So what does this tree say? This tree says, well, you have as a root a get operation, and you have two possibilities. You have two children, and on the left you have put F, which is another operation that you have performed. On the right you have get T, we have put T, and as the leaves you have the value that is returned from this computation. Right? In this case you will return T, and in that case you will return F. So now we have actually drawn a computational tree that corresponds to this program. And now I can even write a program with just a tree. Right? I don't give you the program. And here is a tree that corresponds to this program. Can you tell me what this program is doing? Mm-hmm.
If you get, oh,
Oh, isn't it like non-deterministically erasing error?
How about the other branches? You have more
Oh,
choices.
okay. If you end up with true, then non-deterministically you erase an error. But if you get false, you put T and get an F.
Right. So you try to get the value of that memory location, and if it's true, you will non-deterministically either raise an exception or just return what the value is stored in that location. And if the value stored is false, you will just put back true and then return F. So basically, this function returns whatever is stored currently in this memory location and try to put it back to true. But it might raise an exception when the value is already true. So you can also write the program out, right, using the set of operations we have seen. So I hope this gives you some intuition about computational trees and effectful computations. And for people who have heard about the terminology interaction trees are basically co-inductive versions of computational trees. Yes.
So, is it true that the computation is the simplest and
What?
for the effect of computation, it looks like the computation tree is also the syntax tree of the yes.
Yes. It's a way to represent the computation as syntax tree. You can do it that way. Yes. Yes.
But the T and F above the line, above the line connected to get, is related to the semantics of get.
Very good point. These labels are not necessary. Like I just put it there for you.
Hi, sorry to miss the thing. Are the T and F in the triangles, are those continuations?
These triangles are values, and rectangles are operations. So this basically saying like if you do this and that, and in the end you may return, you will return T. Okay. I think I will very quickly talk about free monads in the rest 3 minutes. Because free monads are, well, it's not the focus of the part, but in case that you have also heard about these words, this terminology, you can also represent computational trees as free monads. Basically, it has a definition like this. It's like very recursive, but it's basically a tree if you consider this pew as the node of the tree, and you consider all those recursive trees as the operations that produce another free computation. So basically, all those children that you would have, which are themselves also computations, and then in the end, you will terminate with the pew, which is the leaf of the computational tree. It's called free monad because as long as f is a factor, you can give a monad definition for it. And then, in which case, the return is just this pew, and the bind operation will perform substitutions at the leaves. So if you try to say, okay, let's return C and then do R, then this R will just get directly mapped to the value. But if you have some set of operations in this, like you can consider it as the recursive free case, but I wrote it in the syntax that we have seen. It's basically pushing what happens afterwards to each node. So you can also see the relation between this definition to the part of the algebraicity we have seen. So it's basically folding over the computational tree and apply this computation to all the leaf nodes of the tree. So I don't think I have time to talk about generic effects. So we will cover that in the next lecture, but generic effects are basically a better way to program with algebraic effects, but they are equivalent to algebraic effects, and generic effects are usually what people actually implement in programming languages, and then also in all the research programming languages that we have seen. And afterwards, we'll talk about effect handlers. Yes?
So can you go one slide back? So in general, you can construct a fixed point like this, right? Like it depends on, f has to have certain properties. Like
f has to be a factor.
No, that's not enough. Like f has to preserve colimits.
What?
Because you need to construct a fixed point like this. Not any function will have this property. Like if it has mixed variance or something, you would not you wouldn't be able to construct this function.
I'm not sure I get the question.
I'm just saying here, like it's not enough that f is just a function in order to construct this fixed point.
Which fixed point?
Like you have this data free FA, and then the data type itself appears as a recursive instance on the right.
Right.
It's not enough that it's just that f is a functor. It has to preserve colimits as well.
It has to
Preserve colimits. So in particular, if you have mixed variance or something, you're running into it. Well, no, that's not even it. Like even some cases where you have just covariance, it's not enough.
Okay, maybe we can talk it out.
Yeah,